Hi, welcome to this next video on the part where I'll be talking about waves and optics. This topic is quite short, so I don't think this video will be too long, but it kind of covers a range of things. And the questions can be quite tricky in this topic. So I feel like the syllabus kind of spoke about these things slightly out of order. So I wanted to talk about the terminology first. So when it comes to describing waves, we have several different terms I'm sure you're already aware of, but it's just important to kind of refresh our memory, I think, and talk about these things because you probably did this last year in year 12. And if you're applying in a gap year, then you probably did this ages ago. So first term is amplitude, and I'm sure you're all aware is the height of your wave. And then your frequency would be how many waves occur per second. And then your period is the inverse of the frequency, essentially. And it's the time that it takes for your wave to complete one full cycle. And next is your wavelength, which is the distance between peaks or the distance between troughs, but essentially the distance between 2 points of the same phase in your wave. And then your wave speed describes how fast a single point travels in the direction of the wave. And finally, your wave number is something you may not have come across, but it's essentially the space equivalent of your frequency, and it describes how many waves occur per meter. So if we look at a little graph, we can see here that if we plot our waves height against time, so this essentially plots out an oscillation, then our amplitude is the maximum distance away from this kind of equilibrium origin point. And then our period here is the time taken to complete one full wave. And then here we have a second graph, which shows the kind of like spatial representation of a wave. So this might be a mapping of a wave at a certain time t. And you can see here that the amplitude again is the furthest displacement from the origin. And then our wavelength this time is the distance between two consecutive points of the same phase. Just some other useful words to point out. Nodes are points of zero displacement. So like the place that I've dotted there. And then I've been using this word phase quite a lot. That just describes where in its cycle it is. So say at this point here, it's a quarter of the way through its cycle. So its phase would be 90 degrees. Okay, so this next point on the syllabus was longitudinal and transverse waves. This is quite a vague title on the syllabus, but just be sure that it's important to know the difference between a longitudinal and a transverse wave. I'll try and put some kind of an animation or something in here, but I just found a question on waves and I will go through that. So this question describes a small boat floating on the sea and it encounters a wave of this form. And it's telling us information about these two graphs here. So say we hold t constant, then we can get this kind of spatial representation at a certain time. And then say we hold this x constant, then we can get some kind of a like wave representation, looking at the kind of time portion, how it changes over time at that point. So they tell us that we have a wavelength of 10, an amplitude of 0.5 meters, and horizontal speed of 2 meters per second. So that is the equivalent of this wave speed C here, which describes a point and its speed across like that. So how quickly that point would move across. And it wants us to work out what the maximum vertical velocity of the boat is. So I've just written our information down here. This is our equation. These are the constants that they've told us. And in this case, it's important to kind of put our calculus hats back on. We always seem to be putting our calculus hats on. But when they're asking for the maximum vertical velocity of the boat, we need to know what the vertical velocity is actually related to. And the vertical velocity would be the rate of change of this vertical displacement y here. So in other words, dy by dt. So if we just go in and do that differentiation, then we come out with this equation here, remembering this negative here. So after doing that differentiation, we end up with minus a omega cos kx minus omega t. And at this point, we need to think about what we know about a cos function. We're after the maximum vertical velocity of the boat, and our value for cos kx minus omega t, whatever is inside those brackets really, is always going to be ranging from 1 and minus 1. It can't exceed 1, it can't exceed minus 1. So looking at this equation here, then we can say that our maximum value happens when cos is minus 1, or 1 if you are just looking at the magnitude. So that means we know that our maximum dy by dt is a omega. So we have some numerical values for this. We know that our amplitude is 0.5. We were not explicitly told what the angular velocity omega is, but from knowing that omega is 2 pi f, and we also know that the speed of a wave is equal to our frequency multiplied by our wavelength, and we know the speed of the wave and we know the wavelength, so we can rearrange this for the frequency and pop this back into this omega as 2 pi f to get omega is 2 pi c over lambda, and then we can just multiply these two together, stick the numbers in, and we come out with pi over 5 meters per second. Right, so this next part of the syllabus discusses the understanding that waves have no net movement of matter and standing waves. So I picked a question here about standing waves. It's a multiple choice question, and it asks, a stationary wave is set up on a string of length L. If the center and the ends of the string are held fixed with a zero displacement, what wavelengths, lambda m, can this stationary wave have? And then we have some options of answers. Oh, and m can't be 0. So if we think about what's happening here, we have a string, and it's been clamped in 3 locations. It's been clamped at the origin, it's been clamped at the center, and it's been clamped at the end. So essentially, we can just kind of look at this half, well, either half really, but I'll go for the left half to see where the modes happen. So we have this, technically this mode 1 here, which, if you remember what your mode shapes look like, then mode 1 would be like this with essentially 1 half wave in it. Our mode 2 would look like this with 2 half waves in it. Our mode 3 would look like this with 3 half waves in it. So essentially, we have 1 extra half wave at each mode. So this length over here is L over 2. So our first wavelength, so essentially this is a half a wavelength here, so the full wavelength would be L. And then our second wavelength is one where we have 2 half wavelengths in this L over 2 side. So that means our full wavelength is L over 2. And then finally, we have this 3 half wavelengths, but in this L over 2, remember. So the wavelength here would be 2/3 of this L over 2 length, which is L over 3. So we can see that we have a progression here that goes L, L over 2, L over 3, next would be L over 4, etc., etc. So it would be this option here. Lambda m is L over m. Okay, so this next question is actually from 2020. So I didn't have any pre-done solutions to compare this to. So if you have any disagreements about what I've done here, then do let me know. But essentially, this question requires us to remember the order of the electromagnetic spectrum, where the long and the short wavelengths fall, and to recognize what wavelength each of these will represent. I just have done a little information board here. This is how I remember the electromagnetic spectrum's order. It's such a dumb way. It's gut. That's how I remember. And gut tells me that it is in the order of radio, micro, E, infrared, V, visible, ultraviolet, X, X-ray, and gut, gamma, so umivugska, radio waves, microwaves, infrared waves, visible light, ultraviolet light, X-rays, and gamma rays. And this is from long to short. And I feel like the best way of remembering which side is long and which side is short is to think about how high or low energy your waves on the spectrum are. So gamma waves are super dangerous, right? Because they're so high energy that they just ionize things really easily. So I remember gamma is high energy, and they're high energy because they oscillate really fast, like this. And then I remember that radio waves are super safe because they're everywhere. They're low energy and they're slow because they oscillate really slowly, like this. So our radio waves are our long wavelengths and our gamma waves are our short wavelengths. So now we need to take a moment to think about these implements they've given us and what sort of radiation they release. So the first one is an electric torch. And if we think about what that does, it shines light for us to see, right? So it releases visible light. Then the next one is a microwave oven, and I think there might be a slight clue in the name there. They release microwaves. Then the next is a radioactive source. So I've kind of discussed this. Super high energy radioactive dangerous substance is controlled by a gamma ray. And then a hot cooking stove, what does that produce? It produces heat to cook things. And the section of the electromagnetic spectrum that relates to heating things would be infrared. If we think about an infrared camera, it tracks the heat of your body. And then finally, a shortwave radio transmitter. I think, again, that has a slight hint in the name. It transmits radio waves. We need to be careful that we go from shortest to longest, like they're asking for. So our shortest wave was this gamma here, so number 3. So we definitely start with 3. And then our longest wave was our radio wave. So we're definitely ending in 5, and then just filling in the gaps in the middle. I have 1, 4, 2, and thankfully this is one of our options. This is A. Okay, so this next section is about refraction and Snell's law. And the first part of this is that they want you to write down Snell's law. So what they're asking you to do is write an expression relating the angle of incidence and the angle of refraction of a light traveling from one optically transparent material with refractive index n1 to another with index of n2. So that is just Snell's law, right? And that's probably 1 mark. And then next they want us to sketch a diagram of the ray, clearly labeling the angles and indices of refraction. And they want us to say under what conditions the light is completely reflected inwards at the boundary. So here's a little sketch here. We have this ray of light traveling from I decided to go from a more optically dense substance to a less optically dense substance. And you can see that because this ray here is traveling slower than this ray here. And we know this because I don't know if you remember it the same way as me, but we speed away. So if our angle is greater, then that means we've sped away from this perpendicular line to the boundary. So we're traveling slower when we're closer to this perpendicular line, and we're traveling faster when we're further from this perpendicular line. And then the next part, they wanted to know under what conditions total internal reflection occurs. And for this, we need to know what the critical angle is. So our critical angle θ1 happens when θ2 is equal to 90 degrees, because that is when this is wide enough such that this just travels along the boundary here. And then any angle greater than that, this angle will be more than 90 degrees, so it'll come and reflect back this side. Using Snell's law that we wrote down earlier, we can say that n1 sine theta c is equal to n2 sine 90, which is 1. And then we can rearrange this to get an expression for the angle down here. Right, so next we have another multiple choice question where we are looking at two mirrors that are at right angles of each other, and there's a beam of light being sent in at some angle A, and we need to decide at what angle it will exit. So I think the easiest way to look at a question like this is to actually just draw a sketch and see what happens. So we have two mirrors that are 90 degrees apart. Then we have this perpendicular line here. And then our angle of incidence is A, and we'll say that that's more than 90 degrees just to give us a visual. So our reflection also must occur at A degrees there. And then we know if this is 90 degrees, then this angle here, and this is 90 degrees here, this angle here would be 90 minus A. We also know that this angle here is 90 minus A, and technically this one as well. And then if we are reflecting off this mirror as well, then we're going to reflect off this one at 90 minus A as well. So we want to work out at what angle these are traveling. And if we take this to be some kind of a datum where we start here and then go around like so to work out our angle, then this angle is essentially happening here. So that is at 90 minus A degrees. So our angle in is 90 minus A. And then our angle out would be this 180 degrees here, plus this 90 minus A. So we can see that they're exactly 180 degrees apart, which is answer B. So the previous question, we tackled some total internal reflection there. And this next point on the syllabus is to do with total internal reflection. So this question, it wants us to explain what is meant by total internal reflection and the critical angle. So we've just kind of tackled it there. We said that the critical angle is when this angle of incidence causes a 90-degree refraction on the opposite side. So our critical angle is angle θ1 such that angle θ2 is 90 degrees. And then total internal reflection causes when our θ1 is greater than this critical angle and the ray reflects internally rather than refracts through to the next medium. So next it wants us to derive an equation relating the critical angle and the refractive indices of the two materials. So we did something similar in the previous question using Snell's law. Okay, next we have an optical fiber and it's made from two materials. And they want us to work out what this maximum angle is such that we have total internal reflection in here. So we need to take this step by step. In order to get total internal reflection on the inside, we need to make sure that we exceed this critical angle between these two media. Our sine theta critical is the optical density of the cladding divided by the optical density of the core. And then next, we can see that this refracted angle down here would be this critical core angle here would be 90 minus that critical core angle there. So if we want to work out the sine of the angle of refraction, then that is the same as it being the cos of this critical angle. And that's because if we imagine what's happening here, if we take the sine of 90 minus theta critical, we've shifted this 90 degrees to the left, and that is the same as saying that it is cos of minus theta critical. But we also know that cos is an even function, so whether this is plus or minus, we'll still get the same thing. So we can say that that's cos of the critical angle. But knowing the cos of the angle is not particularly helpful because Snell's law only really talks about sines. So this is where we need to use some trigonometry, and the relationship of sine squared plus cos squared is equal to 1. So we know that sine squared of our critical angle, well, we know the sine of our critical angle is n clad over n core. So that squared would be n clad over n core squared, plus this cos squared of the critical angle. Then we can rearrange to get an expression for cos theta critical. And we know that cos theta critical is the same as the sine of theta refract. So we can say that sine theta refract is √1 minus n clad over n core squared. And just to reiterate, this n refract is this n refract, or what I've called n refract, is this little angle here. So after it's come in from the air to the core, the angle it was refracted to. So we have an expression for that. And then we can use Snell's law to relate the angle of incidence onto the core. So this theta max. We know n air is just 1. N core, we know that's n core, and we know sine theta refract from this expression here. So we can just plug in that to get an expression for sine theta max, and then if we take the inverse sine of both sides, theta max. Okay, next we've been told that we've put a little tub of water here, and it's exactly on this face here. So there's no air between the end of the core and the water. And we need to sketch out what our beam coming out will look like. So initially, when it was just air, we had this line here of light that just kind of refracted outwards like that. But now we have this water in front of it. So this beam of light will slow down in the water. So it'll become, the ray will shift closer to this perpendicular line. And then coming out, it will speed back up again. So it will cause a narrower spot of light here, if you will. And then next, they ask us what will happen if instead of using a laser, we used a white light. So this suggests that we have a light of all frequencies being shone through. So with lights of different wavelengths, that means the refractive indices will change. So we'll end up with this kind of like rainbow fringe around from this kind of dispersion of the different wavelengths. Right, so this next topic is about interference and diffraction. And we're told that we have a monochromatic point light. So we have a point light at one wavelength, which is shining through two narrow slits. I'm sure you've all come across this experiment with the two narrow slits, but it's essentially a demonstration of constructive and destructive interference, and they want us to sketch what the image on the screen will look like. So we have light that's been dispersed through these two little gaps here, and this diagram, I'm sure you've seen it before, but it tracks points of the same phase, if you will. So this probably looks something like this, actually, and we're tracking the peaks here. So where these lines cross from the two different slits, those would be where peaks meet peaks, and essentially where constructive interference will happen. And then we're kind of like the middle of these two lines are in the space. Those would be where two troughs meet, so that would also be constructive interference. And then where a gap here meets a line here, so the gap in the middle of the two lines meets a line, that would be where a peak and a trough meet. So we would have destructive interference, which would cause like dark spots. So on this screen over here, we'll end up with bright spots that fade as the ratio of constructive to destructive interference increases or decreases. And we end up with these kind of like bright bands of fading. So next they say, if this corresponded to a red light, what would the pattern look like for a green light sketch on the same scale? So red light has a longer wavelength than green light. So for a shorter wavelength, it would mean that we have more of these peaks closer together. So that means that these bands will occur closer together. And this next question is kind of a similar idea. It's referring to constructive and deconstructive interference, but this time for sound rather than light. and it's saying if we have this loudspeaker here, and then these sound waves hit this screen and then bounce back, and we have a microphone over here to pick up the sound that occurs, would the microphone record maxima and minima if the loudspeaker or the microphone is moving along the x direction? And then they're also asking how far apart this loudspeaker and the screen need to be in order to, or between two successive maxima. Between the two successive maxima, this would be where a peak and a peak meet. So those occur one wavelength apart, and also where a trough and a trough meet. So those also occur a wavelength apart, but a trough and a trough will occur half a wavelength away from a peak and a peak. So that means we'll get constructive interference every half wavelength, as I popped here. Okay, so the next part is if the loudspeaker is moving, will it record maxima and minima? So in order to understand what's going on here, we need to kind of look at this diagram in two different ways. At the moment, we're looking at it as a still image. We're looking at it as essentially we are in one fixed position. And this one fixed position here is where maxima meet maxima and or peaks meets peaks at the moment. So this would be a point where we hear a maximum. But imagine we've shifted this screen slightly to the right. So then it means that our lines, these like reflection lines, will have moved along like this. So they might be here at a certain X distance. And at this point, peaks no longer meet peaks along this axis where the microphone is. So like say something like this, the peaks miss the peaks and they might hit the troughs instead. So it will hear maxima and minima as these kind of like reflection lines move. However, if the microphone is moving, that means that these reflection lines stay matched up to a certain position with these transmitted lines, if you will. So that means as the microphone moves across, if we imagine this is a little microphone here now, as it moves across, it still meets maxima at all points. There is constructive interference all the way across this path here. So it will not hear maxima minima, it will just hear, if the loudspeaker and the screen are in a position where the peaks and the troughs are meeting, then it will hear constructive interference the entire way. And if the loudspeaker and the screen are in a position where they have destructive interference the entire way, then it won't hear anything. So the answer to our question are, if the loudspeaker is moving, then yes, the microphone will hear maxima and minima. And if it's a microphone that moves and everything else stays still, then no, it will not hear maxima and minima. So finally, this question, I remember this one being quite tricky, but it's a question, it's more of a maths question actually than a waves question, but I think it's important to know how to use information that they give you effectively. So here we have two waves, but they're essentially just two graphs, two cos graphs that give us some information about x and t again. And first of all, they ask a question that is quite unrelated to this information here, so probably worth like 1 mark. But they're asking what the speed in terms of angular frequencies and wavelengths. So we just need to think of our equations for the speed of a wave. I always remember this as c equals f lambda, but in this case, they've called the speed v. So v equals f lambda. And they want it in terms of the angular frequency. So we know that the angular frequency omega is equal to 2 pi f. So we can replace this f here with f equals omega over 2 pi to get our speed to be v equals omega lambda over 2 pi. You may have to say v1 is omega 1 lambda 1 over 2 pi and v2 is omega 2 lambda 2 over 2 pi, but I did not bother because I'm not being marked. Right, so the next part, the sketch y1 plus y2, is possibly the more complicated part of the question. But the important part to notice here is that they ask for it as a function of x at some time t. So that's telling you want an xy graph. And it's telling you at some time t, it is essentially a kind of displacement image at some time t. So personally, I decided to just say that the time was 0, but you could use any time that you wanted to, but 0 just helped uncomplicate things for me a little bit. But essentially what they're telling you here, at some time t means t is irrelevant. And they've given us a little expression down the bottom here to tell us how to add two cos functions. So they say cos x plus cos y x is equal to 2 cos x plus y over 2 multiplied by cos x minus y over 2. So I've decided to take the amplitude out and say that x is what's inside of this bracket here. So 2 pi x over lambda 1 minus omega 1t. And then y is what was inside this bracket here. So the same thing, but with lambda 2 and omega 2. And then the two constituent parts that we need are x plus y and x minus y. So I've just worked out what x plus y and x minus y are here individually. And then I've plonked those values into here, remembering to divide by 2 as well, because it was cos x plus y divided by 2 and cos x minus y divided by 2. So we end up with these values inside of our causes. And at this point, we need to remember kind of what's happening and what we're being told. What we're told out here is that our amplitude is 2a. And then we have one cos graph here. So that will be a cos with some kind of a frequency. And then the second cos here with a different frequency. And we can work out what the wavelengths of these two cos functions are, remembering that a wave would be in this form, where the prefix to our useful function, I suppose, would be omega. And then we have some kind of phase difference here. So we can say that, at this point, I've set time as 0, just to look at it at one kind of time image, well, one still image. And I can say that omega is equal to the coefficient of x here, which is for this first side is pi lambda 1 plus lambda 2 divided by lambda 1 lambda 2. So down here I've said omega is equal to that, but we can also remember that omega is equal to 2 pi over lambda. And then that can give us an expression for the wavelength. And then we can do the same thing for the other cos function. And since the first one has a lambda 1 plus a lambda 2 on the bottom, and the second one has lambda 2 minus lambda 1 on the bottom, then it means that that lambda a, as I've called it, has a larger bottom, so is a smaller number. And lambda b, as I've called it, has a smaller bottom, so it's a larger number. So consider 5 over 3 would be larger than 5 over 4. And then essentially what happens when we multiply two different cos functions is, so say we sketch out these two cos functions first. We end up with something that looks like this. We have a wave with a shorter wavelength, this kind of red one here. And then we have a wavelength with a longer wavelength, this green one here. And as we multiply these together, the longer wavelength acts as a sort of changing amplitude to the shorter wavelength. So if we multiply these two together, what we'll get is we'll get this 1 times 1 here, and then we'll get this value multiplied by this value. And then if we keep going, say at this point down here, we have a -1 multiplied by whatever this value is here. And we end up with this kind of sinusoidal amplitude, if you will. So now it's asking, if you stood in the path of these sound waves, what frequency would you hear? Well, essentially what's happening here is this is a wave of this short wavelength, but its volume is changing sinusoidally. So we would hear a wave of this short wavelength. And it's also asking where the sound disappears. So the sound will disappear at each node of the longer wavelength. So the frequency that we hear is the frequency of this smaller wave, which we can work out from the speed of the wave and the wavelength. And there are kind of two options of speed that we can choose here. I'm not really sure which one is correct. I think both are right, to be honest. And then the distance between the nodes would be this longer wavelength, so this wavelength, but divided by 2, because that would be the distance that the node, how far the nodes are apart from each other. We end up with these answers. So thank you for paying attention this long. If you made it this far, congratulations. I look forward to seeing you in the next video where I'll be talking about electricity and magnetism.